Let me point out to you the 4 series that you have here. One thing is straight equal sign versus not straight equal sign. What do you see as the primary difference there? What makes the squiggle equal have to be squiggle equal? Yeah. So it could be just plain set equal to a sigma that goes to infinity. But if it has this plus dot, 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 this is the formula from here on out plus dot, 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 that means infinity. It implies infinity. And especially having this at the end. If it cuts it off here, it needs to be squiggle equal. Oops, I put that in the wrong spot. If it cuts it off here, where you don't have plus dot, 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 that has to be squiggle equal, just to let you know. That wasn't the most important thing. Now, the next thing I want to ask you is, can you determine the center of the power series that is representing each function? What is the center? And the center basically means the x-coordinate of the point of tangency, so to speak. Where is it centered? And we've got 4 of them, so hold on. Maybe I'll put a number 1, 2, 3, and 4. For number 1, what is the center of that polynomial? The a, or the center, is -1. And I want you to see clearly the difference between that and number 2. And number 2, I can see that some of you see it. The center is 0. Notice the difference between when the center is 0 versus not 0. For the third one, the center is not 0. The center is 2. And then for the last one, do you see that the center is 0 for that last one? The Taylor formula in general is nth derivative at the center over n factorial multiplied by x minus the center to the n power. The key is right here. And I'm trying to highlight an emphasis. So if you have any questions on how to determine what the center is, take a good look right here and see when you're centered at 0, you don't have x plus or minus a number. You just have x with the exponent following right there. Even if the exponent follows a particular pattern that isn't just every single exponent, but there's a pattern to them where it skips some of them. The center is an issue of what's in the base, not what the exponent formula is. You're looking at the base, not the exponent for the center. Now, if I asked you for G, I'm going to erase this column if that's all right. I'm going to erase the column of this is what the center is. And get these highlights out of the way. Let's look at this one. If I asked you to determine the third derivative at 0, can you tell me, oops, that's G. I'm too used to writing F, which is not a good thing. Okay, what is G triple prime at 0? Do you know how to find it? If a polynomial is being used to represent a function, then this must be true. So if I put it in terms of G, if I want to know, let me first put it this way. If I know that my center is 0, then I'm going to replace all of my A's with 0. And I'm not going to use a parentheses. I'm just going to say x to the n. So that's if I'm specifically dealing with the center of 0. Now, if I want to know the third derivative, that means this number needs to be a 3. And the only way you're going to see that is if you look for where do you see x to the third power. And the coefficient formula alone, the coefficient of x cubed is positive 3. That positive 3 must be equal to this formula with 3 plugged into the n. So the third derivative, which I can write as triple prime instead of writing the numeral 3 in parentheses. They both mean the same thing. So if I want to know the third derivative at 0, I actually need to multiply both sides by 3 factorial. And 3 factorial is 6, so 6 times 3. And then I saw that a lot of you got that. Now, you can do the derivative 3 times. And let me see, what's that saying? I'm not sure. Okay. And so there you go. Now, I'm going to ask you a trick question. Are you ready for a trick question? I'm even warning you that it's a trick question. I'm warning you ahead of time. Trick question. What if you were asked to find the third derivative at of g, mind you, this is g, at 1? And I'm going to clarify a little bit more in a moment, but I just want to throw that out there very vaguely. What if you were asked to find the derivative of g at the third derivative of g at 1? And then let me clarify the instructions. The instructions for this would have asked you to either find the exact value of the third derivative of g at 1, or explain why you cannot find the exact value of the third derivative of g at 1. And so with that, the answer would be you can't. And I've seen this show up on free response problems in the deep past. So you can only find exact values at the center. Exact values of a function's derivative of any order. And the order of the derivative is referring to, is it first derivative, second derivative, third derivative. So the exact values of a function's derivative can only be found at the center. Any other x-coordinate is an approximation. So realize that if you are asked to find a third derivative or a fourth derivative or a first or a second derivative, any order derivative, they will be asking you to find it at the center. And if they aren't asking you at the center, you can only approximate for that value. You cannot find the exact value. Hand? Yes.
I have a question kind of relating to the problem you just did.
Uh-huh.
So how come we use that third term where n equals 2 to find the third derivative? Wouldn't it be like the one after 3x squared?
Are you referring to g and this? So
wouldn't n equal 2 be that value?
You're looking at, if you want third derivative, that comes from the n being a 3. You might have some pattern stuck in your head. Shush. You might have some pattern in your head from something you've seen.
But isn't for that, wouldn't like for the x value, wouldn't that be for n equals 0, and then the next for negative 3 half x squared for n equals 1?
So that's actually a good question, because I want you to notice what you don't have here. When these polynomials are given to you, they will always be given to you in ascending order. And that means the first term is the constant term. And I don't have a constant term on this one. So if I'm looking at its matchup with the actual Taylor formula here, then this is when n is 1, this is n equals 2, and this is n equals 3. The n value of the Taylor formula matches the exponent if it's specifically referring to the generic Taylor formula.
So if there's no constant term like given in the function, we just kind of assume that the first one is actually for like n equals 1.
If you're matching it with the generic Taylor formula over here.
Okay, gotcha. thank you.
Yeah. And what's tough is to realize that the choosing of the n that is used in the formula, you can actually start at another n. You don't have to start at n equals 0. You don't have to start at n equals 1. You can decide where you want to start. But if you're doing a matchup with the Taylor formula, whatever the exponent is that you see, that's the n number, referring to the Taylor-Maclaurin formula. But you could take any of these polynomials, you could shift the n, and that would shift the formula. So that kind of throws a little bit of a frustration in that you guys have to deal with. But over time, you're going to make more and more sense of this. Yes, and in fact, let's say I just throw out some random formula. I'm just making something up. Yeah, why not? Just make it simple. Okay, let's say this is the formula that you have. Are you ready? Okay, here we go. This is equal to, if I decide that I wanted to write the same exact series, but I'm going to start it at a different n. Let's say I decide I want to start it at 1. So I am adding 1 to my starting n. I can compensate by substituting into every n that I have the compensation of adding 1, n minus 1. So then if I want that same formula to have the first term that came from 0 be coming from a 1, then I replace every n with an n minus 1. But where it can get a little bit confusing is in something a little bit harder. Yeah, I'm just having fun with the formula now. So if I want to shift this, where I'm starting at n equals 1, again, I had to add 1 to go from the 0 to 1. So everywhere I see an n, I want to replace it with the compensation of subtracting 1. But the 1 has to subtract directly from the n. So then that formula is going to be negative 1 to the n minus 1. That's a minus sign, trying to be a minus sign. But now this is x to the, be careful, I'm going to write it here. It's 2 times n minus 1 in parentheses and then plus 1. So that means it's going to be 2n minus 1 altogether. And then underneath here, I'm replacing the, I just did the wrong thing. 1 second. I'm substituting n minus 1. There we go. So the 3n is 3 times parentheses n minus 1. And now they are identical. And so you can take any sigma formula you want and shift it any number of units you want either direction using that idea. But when it comes down to when a polynomial represents a specific function, where did it go? This formula reigns. Whatever exponent you are looking at, that is the number that needs to be the n in the Taylor formula. If you want to know the function it is representing, information about that function it's representing. Okay, now I'm going to erase some of this stuff and then ask you some more questions. Come on, erase. Or don't erase. You can be that way. Okay, perhaps it's a lag time issue and I need to erase slower. Okay, now I want you to look at the h function. And I want you to tell me the second derivative of h at x equals 2. And then to double check that everyone sees why it's negative 18. According to the Taylor formula, whatever my function is, it is equal to the nth derivative of that function at the center over n factorial x minus the center to the n power. And every single term is created this way. So if I want the second derivative of h, then I need to look at when n is equal to 2, what was spit out of this polynomial. I'm looking for, I'm looking for the 2 exponent, because that then must be equal to the second derivative at the center, which is 2, over 2 factorial x minus the center squared. And then if I focus on the coefficient, what you want to be able to eventually do is quickly turn to this coefficient formula. You want to grab the coefficient that you see, including the negative sign if there's a negative sign with it, and set it equal to this formula. Then all you have to do is multiply by 2 factorial. And you've got your second derivative at the center. Okay, now I have another question for you, and I'm going back to the h function again. What is, I'll put it right here, what is h prime of 2? I'm going to erase the work that I did for h double prime of 2. When I look at the polynomial, I see that I have a constant term that comes about from n equals 0. But my next term is squared, and that comes about from n equals 2. I am missing having a term for n equals 1. But when a function is being approximated through a polynomial, the only way for that particular term to not show up is if its coefficient is 0. And when I look at, let me write this out. So when n is equal to 1, that means first derivative at the center divided by 1 factorial equals x minus the center to the 1 power. If that's equal to 0, that's only because the first derivative is equal to 0. So if a term is missing, you know that that order derivative at the center is 0. So h prime of 2 is 0, and h double prime of 2 we got as negative 18. Can you then tell me the answer to this question? Does h have a relative maximum, a relative minimum, or neither at x equals 2? And justify. And I just realized I wrote positive 18. It was negative 18, wasn't it? That kind of matters. So if you're getting a negative second derivative, then you're dealing with a concave down graph. That was a terrible drawing. That's a little bit better. And if you have a 0 slope, that's only going to happen when you are peaking at a relative maximum. So your answer to this question is relative maximum, because the first derivative at that number is 0 and the second derivative at that number is negative. And it is by the second derivative test. It's good to name the test you're using, because that clears up all justification issues. I've got another question for you. Are you ready for the next one? It doesn't matter. It's coming your way anyway. Ha ha ha! That was supposed to be funny. Whether it was or not, I don't know. Happy Monday to you all. Happy Monday. Getting rid of all this. Okay. Next question. Does g of x have a relative maximum, relative minimum, or neither at x equals 0? And make sure to justify your conclusion. Don't look at chat if you don't want the answer. So when I have the understanding that that x is x to the 1 power, and I match it to the Taylor formula when n is equal to 1, then these must be equal. That means the derivative of g at 0 must be equal to the number 1 in order for those two to equal each other. If the derivative at a number is not 0, and it is actually defined, then it is not a critical number, and it is neither. So neither, because g does not have a critical number, does not have a critical number at x equals 0, and it's not a critical number because the derivative of g of 0 is 1. And that justifies neither. And also think about the logic of it. If something is in the middle of heading up, so if my tangent line has a slope of 1, imagine the different graphs you could draw. Here's a point that it shares. If it's on its way up, then it's not at a highest, and it's certainly not at a lowest. It might reach its highest point soon, but it's not there. So you don't have a relative maximum there. Then these are the big issues that I wanted to make sure to clarify for you. Now, for homework, I already put up the next homework assignment. I don't need to go over any new material for you. It's just continuing to practice what we have. Then my question to you is, did you have any questions on homework 10? And I do want to make sure that everyone is clear about why 3 is written the way it is while I'm at it. Okay. And then number 4 also. All right. So, and let me know if for anybody who needs to see more, I'll get through as much as I can get through before class is over. So if you look at just this expression here, that is undefined at 0 because I'm dividing by 0 at 0, so we've got a problem. Do notice, though, that it is a 0 over 0 situation, which means there's a possibility that it's just a hole in the graph because the limit might exist. But we are being told that for every x that isn't 0, that's what it's following. The 1x, when it is 0, we know that the y value is 1/6. So the big question really is, when x is equal to 0, I know my y value is 1/6. does the function go tra-la-la-la somewhere else, tra-la-la? Or does it go tra-la-la-la, jump, tra-la-la? Or does it go, whoops. Okay, I'm not going to be able to erase the single point, but, or does it go tra-la-la-la, open circle, tra-la-la, and 1/6 fills it in? Because if this has a limit of 1/6, then this is a continuous function. Now, it had to be written this way because if this was the only thing written down, it would technically be incorrect, because we have to be able to have a function that is defined at x equals 0. And its derivative must be defined at x equals 0, and its second derivative, and so on. But the thing is, this function on its own is not defined at 0. So we have to write it as a piecewise in order to make it legitimate. Otherwise, you could just literally be given this formula, and a lot of people would just come up with a series and overlook the technicality and not even be aware that there needed to be a technicality. But that's okay. So don't worry about whether you recognize the technicality or not. Realize why they had to recognize it. Then you can move on and look at the manipulation from there. Do you want me to talk through the manipulation or leave that in the answers? Let me find. Or I can just point out the answers. You start off with sine x multiplied by -1. When you, and very important, when you add a term on, it might change some of the first few terms. But know this. When you put plus ... plus and a formula, that formula is basically saying the pattern you're seeing right before that plus ... is continuing. That's all it's saying. It's not saying this formula works for all n values that are whole numbers. It's basically saying this pattern continues in this manner. When we added x to both sides, it took out the term that comes from when this n is 0. So basically, this formula is now only valid starting at n equals 1, whereas it originated with starting at n equals 0. You don't have to explain that with the formula that you lost a term. You don't have to explain with this formula that the first n we use is 1. When a formula is written out in this manner, if you want to know what the first n is that gets plugged in, look at the first term and figure it out. And that'll be where n starts. And then it is expected that n will then go to the next number up and the next number up and the next number up. So you wind up getting, lost track of where I was at. Dividing by x cubed then takes us to this format. We subtract 3 from the exponent. And that's the only thing that changed in the formula. And then this is the explanation of why that extra bit was in there. And so that should do it for understanding problem number 3. If you have more questions with number 3, let me know. And I'm going to look at number 4. We still have 10 minutes left. Woohoo! So for number 4, I don't remember if I put in more terms than I said in the directions or not, but I mean in the answer key. In the answer key, I might have put more terms than I wrote down there. But basically, what you're going to do is you're going to go 1 minus over 1 plus x minus, and then you're going to put in the first 4 non-zero terms of cosine. So the Maclaurin series for cosine, the first 4 non-zero terms. Cosine is even, so it starts with 1. Then it alternates negative, and it sticks with only even exponents. Then it alternates back to positive, even exponent, and now that's 3, and now that's 4. For e to the x, e to the x starts at 1 and just goes through every single x. X squared over 2 factorial, x cubed over 3 factorial, and so that would be all the first 4 terms. Then, amazingly and brilliantly, we get some cancellations going. We get 1 minus 1, but be careful and distribute that negative sign through. I'm overemphasizing those pluses so I don't screw up. And then 1 minus 1, x minus x, and then make sure you distribute the negative sign through. So the fraction simplifies to a numerator of x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial. The denominator, negative x squared over 2 factorial minus x cubed over 3 factorial, and then that's enough. And it's asking what is the limit as x approaches 0. Now it's asking you to solve the limit through the Maclaurin series, even though you could probably solve this limit a whole lot easier if you just used L'Hopital's rule. What it's wanting you to do is look at the fact that the highest exponent you see is the lowest exponent you see is a 2. So if you divide numerator and denominator by x squared and simplify the algebra, then x squared over 2 factorial divided by x squared, negative x to the 4th over 4 factorial divided by x squared, x to the 6th over x factorial divided by x squared. How do you know to do that? Now you do. I know you like that explanation. If you are trying to work through the algebra of this problem, make this one of the tricks you have up your sleeve of how to work through algebra. When you're dealing with rational expressions, which this is just a massive rational expression within rational expressions after adding together rational expressions. Anytime you're dealing with rational expressions, think about the idea of taking the main fractions numerator and denominator, and multiplying or dividing by the same thing to create something that you can work with, as just kind of a very generic idea, but have that kind of up your sleeve. So then for the bottom, that becomes negative 1 over 2 factorial plus x over 3 factorial. Now when you plug in 0, and that's negative 1. There are much easier ways to solve this limit, but this is just trying to help you learn how to play with your series. The more you play with infinite series, the more comfortable you're going to get with it. And that means playing with it in different formats. Whether you end up testing on a problem where it has limit in it, you'll find out. Ha ha ha. That's all I'm going to say right now. But the most important thing right now is for you to play with infinite series in different formats. And I want you to also recognize that while this only asked you for the first 4 non-zero terms, do you see that you could have looked at all infinite terms? You could have done a plus dot 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 plus and then done a general formula. But every single term after each of these, oops, let me go over here. Every single term from here on out will be 0 when you plug it in. If you were looking at the full infinite degree polynomial, everything would be 0. And it would leave you with just these numbers. So also kind of see how you can actually solve these limits using the full format of the infinite degree polynomial by writing the plus dot 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 pattern. And then let me see what else was asked for. Are the recent did that question get answered? Are the recent terms considered the previous 3 terms? Or is that still a question? I'm just looking in chat and noticing that question that I don't know if I answered. Okay. Oh. Now, as we're in the middle of this, can you see why most calculus students consider this chapter to be the most complicated? But know that you are not expected at this point to feel like you've really got a good hold of it. Otherwise, I'd be giving you a test tomorrow. I'm not giving you a test tomorrow. I'm giving you a quiz tomorrow on just a little tiny bit, and I already showed you exactly what's going to show up. So I'll remind you again. You're going to see problems like from homework number 8, anything like 1 through 3. And I need to see that you do this. I need to see that you do this table. You take all the derivatives with respect to x. I need to see them. You take all of those and plug the center in. And then through that, you write out a first 4 non-zero terms. And this would be the final answer that I'll be looking for in the quiz. So this is just checking to see, do you know how to from scratch, take a function and at a particularly given center and find the Taylor formula that represents it. Then the other questions are going to involve what we looked at today with the recap in, can you determine whether by the first few terms of a Taylor series, can you determine if that function has a relative max, relative min, or neither at the center x coordinate? And on top of that, can you find any derivative order you are asked for? So if I was looking at f of x and I asked you, what is f double prime of -1? What would that be? And it's easy to make reciprocal mistakes. So what I advise is that for now, you write out the formula. The formula says that the second derivative at the center divided by 2 factorial times x minus the center, and the center was -1, to the second power. These matching, and then finding the term that has that exponent. Whoa. Did I just run out of time and people are starting to leave? Okay. So with this exponent, the coefficient is just 1, and it's fastest if you take that number and set it equal to the formula, and then you will see that it's 2. 2 factorial if you want, but set this equal to 1, and then solve. And if there's too much busy work in there for you to see, formula equals coefficient, multiply both sides by 2 factorial, and you get that the second derivative at -1 is that number, which is 2. So tomorrow I want to make sure that you know how to do those few things for sure. But we're not even taking a test this week. We still have a lot to make sense of before we are ready for a test. Yeah, I'm going to give the quiz during class, the second half. All right, then I will see you tomorrow. And if you have questions, stick around.